Hello everybody, we hope you're having a good day and staying safe. This is our midterm senior design presentation. My name is Karen Quevedo.
Lady Luna, Shear Escalante,
Jose Marin.
And we're going to present our topic on bio-inspired UAV two-blade propeller prototype for the RQ-11 Raven. The main focus of the project is to improve the blade, which can be seen in the left to the side of the slide, and we're going to be focusing on the aerodynamics and aeroacoustic performances, so we're going to be taking those into account in order to choose an optimal design. So the problem that we analyze for the RQ-11 Raven, or the area for improvement, is mainly the battery durability and the noise emission. Battery didn't last very long before it needed to return to the operator, and also the propeller was really noisy that maybe it can give the unit's position, and that will be bad for the security of the soldiers. Also, the main goal is to improve the battery life in order to increase the RQ-11's Raven performance of the range of flight.
These are the prototypes that we will be working with. They were all designed with Autodesk Fusion 360 and with the help of Dr. Choutapali by using a method called blade element theory. All the parameters for the design were set. The propellers are 14 inches in length. They all start with a 50-degree angle of attack from hub to tip, and they all have a NACA 0012 airfoil profile throughout the blades. As you can see, Model A doesn't have any bumps or any modifications to the design because we want to compare the results we get from testing with the other models that had bumps. Model B has 4 bumps and Model C has 8 bumps. In this slide, we can see different views of the 8-bump propeller. You can notice the bumps and how the blade progressively straightens out from hub to tip. In figure B, we can see a cross-section of the propeller and we can notice how the angle starts to decrease. The small hole that goes all the way through of the hub in the propeller is said to be 26 thousandths of an inch, and it's that size because it has to fit on the thrust analyzer when we do the testing.
In this slide, we can see the 3 photos of the printing of the original blade. This one has a parameter, as my colleague said, that was approximately 14 inches long, and it's a brick printing. We decided to printing it in PLA because of the situation that we're living. The original idea was to print these prototypes in resin, but due to the situation, it's the only choice that we have for right now, and hopefully for the future we're going to have the other ones.
Market analysis. Today, the RQ-11 Raven is the most commonly used UAV in the world. The most recent order was for $6.4 million in September 2019. The manufacturing cost will not be significantly impacted by the improvement of the blade design. However, the real economic impact comes from the energy saved by the new blade and how much is the customer willing to pay for the improvement that increase battery life and reduce noise. Positioning chart. In the positioning chart, the new design of the blade for the RQ-11 Raven could position the model more close to the RQ-20 Puma in terms of high endurance, solving one of the principal problems without incrementing the cost of production significantly, making the RQ-11 Raven better than the competitors. Process analysis. The process for developing the prototype after elaborating the proper design previously explained starts with the selection of the 3D printing as our method to create the prototype. The principal reason is the accessibility of the source. For the material, the plastic is the most friendly material to print. However, the test will be on a scale that do not affect the plastic. The original model is also printed in plastic to have a fair difference between the original model and our design. However, as my teammate previously said, we had a plan to print in resin if the situation allowed us to do that. Other manufacturing device for this project is a balancer, to prove that the gravity center concur with the rotation. The manufacturing process for this device was metal cutting in lathe machine.
Thermal analysis.
The RQ-11 Raven is component when needed to supply capabilities to undeveloped countries, often in rugged environments. It also includes components such as the digital camera, GPS, motor, and battery, which dissipates heat inside the cabinet. The RQ-11 Raven is also exposed to challenging environments that will be high in velocity, temperature, and altitude, and can cause a failure. This failure can be solved by performing a thermal and fluid analysis of the UAV just to get to know its limitations. One of the limitations found in the technical manual of the RQ-11 is the model can resist a temperature range of -29 to 50 degrees Celsius. Flow. There are significant challenges to perform a flow-only analysis, such as high velocity and the change in fluid properties due to the altitude. These fluid properties can make vibration, also known as turbulence. Now, turbulence from the propeller is usually caused by a mass imbalance. What is a mass imbalance? A mass imbalance is when the center of gravity of the propeller is not in the same location as the center of rotation of the propeller. Some of the flow limitations found in the technical manual of the RQ-11 Raven are the normal operating altitude, that goes from 150 to 1,000 feet above ground level. Also, a cruise rate of 26 knots, range of 10 kilometers, line on sign, and finally, it handles a maximum flight altitude of 10,500 feet mean sea level. Efficiency. Efficiency is a measure of how much work or energy is conserved in a process. In many processes, work or energy is lost, for example, as waste heat or vibration. Considering the RQ-11 Raven is powered by a direct drive electric motor, the electric motor used on the Raven is an Aveox 27267AV with a power output of approximately 250 watts and an efficiency of 95%. This will result in a heat waste of 5%. A perfect process will have an efficiency of 100%. Now, the next point is the efficiency formula. The efficiency is the energy output divided by the energy input and expressed as a percentage. The efficiency is represented by the Greek letter eta. The W out is the work of energy produced by a process. The W in is the work of energy put into a process. With this formula, we can get the exact heat that is waste or lost by factoring out the W out. So we have the 95% that is the efficiency and the W in that is the 250 watts. Now, the first step is to multiply both of those values, the 0.95 times the 250, getting 237.5. Now, this number is the energy that is actually used in the process. So we just need to subtract the 250 minus this value, getting a 12.5 that represents the heat that is lost.
To conclude, the expectations of the blade propeller have not changed. We're still focusing to improve the aerodynamics and the aeroacoustics with the new designs that we just showed you. And in these difficult times, due to the situation that we're living, we're trying to advance as much as we can. So for now, the future tasks is to continue finishing printing the PLA and, if we could, the resin ones, and then continue with testing. And the tests that we're considering are sound and thrust, as we mentioned in Senior 1, and the surrounding ones, which includes temperature and vibrations. So those are the future tasks, but we will see how this moves on.
This was our senior design midterm presentation. If you have further questions, we are going to have a live session. Thank you for your time.